Section 2.7 is on implicit differentiation. So what is implicit differentiation? Look, again, no new derivative rules. We are done with derivative rules. It's just a different technique and allows us to take derivatives of equations with multiple variables. Instead of just something like f of x equals 2x plus 3, we can do something like x squared plus y squared equals 5. So we're going to be able to take derivatives of more complicated equations. So what is implicit versus explicit? Everything we've been doing has been explicit. It's been very clear. Y equals f of x. Our functions have been y equals 3x minus 5, etc. It's very clear which one is the input variable and which one's the output variable. Remember, it doesn't have to be x's and y's. We've just traditionally used x's and y's. So let's read this. It says, so far in the text, most functions involving two variables have been expressed in the explicit form. Y equals f of x. Again, that's the explicit form. That is, one of the two variables has been explicitly given in terms of the other. For example, in the equation y equals 3x minus 5, the variable y is explicitly written as a function of x. Some functions, however, are not given explicitly and are only implied by a given equation, as shown in example 1. So example 1 says, finding a derivative explicitly. Find dy dx, so the derivative of y with respect of x, for the equation x squared y equals 1. And again, anytime you see dy dx, I'm a little lazier. I like using y prime for dy dx. It means the exact same thing. But what's our issue with this? Our issue is we don't have y equals something in terms of x. Well, if we don't have it equals something in terms of x, the question is, can we solve for y in these equations? Well, if we have x squared y equals 1, we could divide both sides by x squared. If we divide both sides by x squared, we would end up with y equals 1 over x squared. This is the explicit form of the of the equation, the explicit form. Again, if I wanted to find the derivative of this, I'd probably look at this as x to the negative 2, though, wouldn't I? So I could use the power rule. So if I wanted to find y prime, which is dy dx, which is what the problem asks for, again, y prime is dy dx, I'd drop the power, so that'd be negative 2x to the power minus 1, so that'd be negative 3. Or we could clean it up a little bit and write it as negative 2 over x cubed. So that's what y prime or dy dx would be in this problem. So that is one way, potentially, that we could solve a implicit formula. And why do we call this original problem an implicit formula? Explicit is y equals. Implicit is when you have both sides or both variables on one side. But again, here we are presuming that y is a function of x. Hence why we're solving for dy dx. We're solving for the derivative of y with respect to x, the change in y with respect to x. Okay. So it says the procedure shown in example 1 works whenever you can write the function explicitly. So we were able to divide both sides by x squared and it worked. It says you cannot, however, use this procedure when you are unable to solve for y as a function of x. For instance, how would you find dy dx for the equations x squared minus 2y cubed plus 4y equals 2? Consider that equation again, x squared minus 2y cubed plus 4y equals 2. Could we do like we did on the previous problem where we solved for y? Well, if you moved x squared, subtract x squared from both sides, you would have negative 2y cubed plus 4y equals, and then you would have something on the right. And then you would say, okay, well, maybe you could say, well, they both have a y, so you could factor out a y, but it still wouldn't work. Same thing with the next equation. If you have x squared plus 2xy minus y cubed equals 5, you can't solve for y on these problems. And certainly if you did solve for y, it wouldn't be a function. Remember, a function is each input has one output. So you might have a y squared, but if you remember in our functions, algebra and functions review, or the functions in line review, anytime you have y to a higher power than 1, you're no longer a function. So y is not a function of x. It says for either equation, it is difficult to express y as a function of x explicitly. To differentiate such equations, you can use a procedure called implicit differentiation. So it's going to explain all of this on the next page, but I want to get at it. What is implicit differentiation? Implicit differentiation is essentially find the derivative just like you would and use the chain rule. So I'm going to go back up and show you implicit differentiation on this one. We're going to go back to the problem with x squared y equals 1. What would implicit differentiation be? Well, implicit differentiation would tell you that the derivative with respect of x of y is equal to, I'm going to put y prime for that. Okay? So what's the derivative of y? It's y prime. And it would also tell you something like, what's the derivative with respect to x of y squared? Well, you need to consider this just like we did with u substitution. You would drop the power 2, keep the inside the same, so this would be y to the first, but then you would need to put that y prime there. So essentially we're just using the chain rule, but instead of using u's, we're using y's. So if you look at this, x squared times y equals 1, how could we do this with implicit differentiation? Well, that's a product rule, right? The product rule, if we look at it, the first function's x squared, the second function's y. Well, the derivative of the first function would be 2x, and the derivative of the second function, well, the derivative of y is y prime, isn't it? Y prime. I'm going to write it as y prime. It's really dy dx. So if I looked at this, you would do 1 d2 plus 2 d1, right? So finding the derivative of the left-hand side, it would be x squared, the first, times y prime, the derivative of the second, plus the second, which is y, times the derivative of the first, which would be 2x. Of course, this is equal to the derivative of the right-hand side of the equation, because all we're doing is finding the derivative with respect to x of the left, and the derivative with respect to x of the right-hand side of the equation, and the derivative of 1 is 0. So this would be x squared y prime plus 2xy equals 0. Well, we can subtract 2xy from both sides because we're trying to solve for y prime. And you would have x squared y prime equals negative 2xy. Divide both sides by x squared. Again, I'm trying to get y prime by itself. And I'd have y prime equals, well, notice one of the x's simplify, and you'd have y prime equals negative 2y all over x. That would be the derivative using implicit differentiation. So if you notice, question is are these two things equivalent? Well, if you remember, what was y? Y was 1 over x squared. So if we substituted y as 1 over x squared, these two answers would be absolutely identical. So if we do it explicitly, we have y prime equals, and there's only x's on the right. If we do it implicitly, we might actually have y's on the right-hand side as well. And that's perfectly fine. So that's the technique of implicit differentiation, is rather than having to solve for y, which we can't always do, because you can't do it in equations like x squared minus 2y cubed plus 4y equals 2. You can't solve for y. That doesn't mean that we can't differentiate using the chain rule, knowing that the derivative of y is y prime. So for instance, the derivative of y squared would be 2y y prime. The derivative of y cubed would be 3y squared y prime. Don't forget that y prime. And then just solve for y prime. So that's the difference between the two. Explicit, it's clear. Implicit, we have to use the derivative of y as y prime, use the chain rule, do the derivative of both sides of the equation, and solve for y prime. You'll see more examples on the next pages.